So the transfer function of electrical network, let us say we have some electrical network like this. We have two impedances, Z1 of S. So this is output V0 of S, and this is input, let us say Vi of S. So obtain the transfer function V0 of S upon Vi of S. That's it. V0 of S upon Vi of S. How will you calculate? How will you calculate the transfer function? You already know the voltage division principle, right? The voltage division rule, right? So V0 of S by Vi of S, how will you get it? It is simply Z2 of S divided by Z1 of S plus Z2 of S. Yes or no? Z2 of S divided by Z1 of S plus Z2 of S. So KVL, KCL, what are the techniques you know you can use, right? So if at all you don't know voltage division rule, you can use this particular principle. You have to calculate I of S first, right? What is I of S? I of S is equal to, the current I of S is equal to Vi of S divided by what? Divided by Z1 of S plus Z2 of S, right? So what is V0 of S? V0 of S is equal to I of S multiplied by Z2 of S. That is equal to I of S multiplied by Z2 of S. That is equal to what? Vi of S multiplied by, Vi of S upon Z1 of S plus Z2 of S multiplied by Z2 of S, right? Therefore, if you just cross multiply, you will get V0 of S. If you bring this to LHS, you will get V0 of S upon Vi of S is equal to what? Z2 of S divided by Z1 of S plus Z2 of S. That's it. Is it clear, everyone? So in order to find out the transfer function of any electrical network, you have to find out the ratio of the Laplace transform of output to Laplace transform of input. The remaining is your electrical network techniques, right? You can use KVL, KCL, anything, right? You have to find out current, voltage, anything, right? So just find out the transfer function of this particular network that I am going to give you and tell me what is the transfer function. Obtain the transfer function of this particular network. So this is C, let us say this is R1, this is R2. Obtain the transfer function and tell me what is the capacitive reactance. Chetkar Kumar, see 1 by omega C is correct only. 1 by omega C is correct only, but see S is equal to sigma plus j omega. If you are ignoring sigma, that is if you are making sigma to 0, you will get j omega only, right? Whenever you are giving only sinusoids, this is valid, that is 1 by j omega C is valid, right? But if we are giving exponentially decaying or exponentially growing sinusoids, then this will be 1 by j omega C will be invalid. So the exact model will be what? 1 upon Cs, right? So this also you can divide this into two different impedances, right? So this is one impedance, Z1 of S. This is another impedance, Z2 of S, right? So what is the transfer function? Transfer function is Z2 of S divided by Z1 of S plus Z2 of S, right? So what is Z1 of S? Z1 of S is the parallel combination of R1 and 1 by Cs, right? So Z1 of S is equal to what? R1 in parallel with 1 by Cs. So obtain this parallel combination, what you will get? It is R1 by Cs upon R1 plus 1 by Cs. So this is nothing but what you will get? R1 divided by R1 Cs plus 1, right? R1 divided by R1 CS plus 1. What about Z2? Z2 is simply R2. Yes, Harsh Sharma, you have calculated it right, very good. Right. So, what is the overall transfer function? V0 of S upon Vi of S is equal to, right, Z2 divided by Z1 plus Z2. What is Z2? Z2 is simply R2. R2 divided by R1. R1 upon R1 CS plus 1 plus R2. Right? So what will you get here? It will be R2 into R1 CS plus 1 divided by R1 plus R2 into R1 CS plus 1. It is R2 into R1 CS plus 1 divided by, right? So if you multiply these two, you will get R1 plus R2 plus R1 R2 CS. You will get R1 R2 CS, right? So you will get R1 plus R2 plus R1 R2, right? The same transfer function we will be using in compensators also. This is nothing but this is a lead compensator network. We will also obtain its transfer function in design chapter also, right? So what network is it? This is a lead compensator. So we'll see much in detail why it is lead, why it is providing phase lead, why not phase lag, and all these things, right? So in this way you can obtain the transfer function of any particular compensator or controller or any electrical network you have, right? So take this as an assignment, obtain the transfer function of this electrical network. Obtain the transfer function of this electrical network. This is V0 of S, this is R2, this is C, this is R1, this is Vi of S. Right? Take this as an assignment. Just take a screenshot or something. Take this as an assignment and tell me the answer tomorrow. Right? Tell me the transfer function of this tomorrow. What is the transfer function? V0 of S divided by Vi of S. Right? So in order to get the practical idea, right? So just to understand the behavior of control systems, let us start our analysis with a practical control system, right? So the best example you can take is your air conditioning systems, right? Your air conditioning system. Let us say you have a ceiling fan in your room, right? If you are feeling hot, what will you do? You will increase the speed of fan so that your sweat gets evaporated, right? So if it is still hotter, your ceiling fan cannot do anything, right? So there what you will do, you will use an air conditioner, right? So let us look at the basic structure of any air conditioner system here, right? So air conditioner, how does it work? Air conditioner has a compressor in it, right? So let us look at the air conditioner example, right? It has what? It has a compressor. A compressor, right? What this compressor does, it compresses air, right? It compresses air, and this compressed air will be used for heat exchange between your room and the outer atmosphere, right? So this compressed air will reject heat from your room to the outer atmosphere, right? So in order to run this compressor will have some pistons and all, right? So there might be a centrifugal type compressor or else a reciprocating compressor, right? So in order to run this reciprocating compressor, there will be an actuator called, a mechanical actuator called an electric motor in your air conditioner. Your air conditioner has a motor in it, an electric motor, right? So this motor is running this air conditioner, right? So because of this compressor, because of the duty cycle of this particular compressor, we are getting a particular output temperature. Let us say our atmospheric temperature, our temperature in our room is some 30 degrees centigrade. Currently, the temperature in the room is some 30 degrees centigrade, right? So this motor is running the compressor, right? So generally, this air conditioner is an automatic system or not, right? So air conditioner is automatic, or else is it manually operated? You tell me whether it is automatic or manually operated. So it is automatic. How? I will explain you how it is automatic. See, what we are doing is we are simply giving an input to your AC, right? So the room temperature is some 30 degrees, but you don't want that 30 degrees, you want some 25 degrees. How much do you want? You want 25 degrees. Therefore, what the user will do, user will specify a reference input, a reference value, that is 25 degrees centigrade. The user will specify this, right? So when user specifies this, the room temperature is not 25 degrees centigrade. So how will this air conditioning system know whether the room temperature has reached to 25 degrees centigrade or not? How will this know? This will have a temperature sensor. This will have a thermometer in it, right? So this will have a temperature sensor, right? So what this temperature sensor will do? Yes, Chetkar Kumar, sensor, very good, right? What this temperature sensor will do? This will sense the room temperature. So I am giving you the block diagram representation only for now, right? So this temperature sensor will give information regarding the room temperature, right, to a comparator. There will be something to compare, right? So you have given 25 degrees centigrade, but the room temperature is 30 degrees centigrade, right? There must be a comparison between both of them, right? So how will you compare two quantities? Let us say Rahul Singh is of some 6 feet, right? Whereas Shivani Sharma is some 5 feet 5 inches, right? Rahul Singh is 6 feet. Is 6 feet tall, whereas Shivani Sharma is some 5 feet 5 inches tall. 5 feet 5 inches tall, right? So how will we compare both of them? How will we compare the heights of both of them, right? Don't mind if I'm wrong with the heights, right? How will we compare both of them? We will compare both of them by computing the difference. What we will say? We will say Rahul Singh is nearly some 5 inches taller as compared to 5 inches taller as compared to Shivani Sharma, right? So we will say Rahul Singh is 5 inches taller than Shivani Sharma. So how did we get this value, right? We have H1 as some height and H2 as another height, right? So how will we compare them? We will compare them by calculating H1 minus H2. We will compare them by calculating H1 minus H2, right? Right. So comparison between two different quantities. How are we carrying it out? By computing the difference between these two quantities, right? So the user input is added at the comparator. User input has a positive sign, whereas the feedback has some negative sign, right? So the difference is going to give some negative value, and this negative value is fed to some intelligent controller within your air conditioner. So what do we call this as? This is controller, right? So this is the overall layout of your air conditioning system, right? So this is the overall layout of your air conditioning system. You have given 25 degrees centigrade as input, right? So this 25 degrees centigrade input is, this first reaches the controller, right? Controller will turn on the motor. This motor will keep running, right? And it will run this compressor. As soon as this compressor runs, right? What happens to the room temperature? Room temperature goes on decreasing slowly, right? So this 39 degrees centigrade now gets down to 30 degrees centigrade now gets down to 20 degrees centigrade, right? When it becomes 20 degrees centigrade, right? 29 degrees centigrade, the difference is again computed, and still there is a difference. This will be fed to the controller. Again the motor keeps running, right? So if the motor keeps running, the compressor keeps running, and again the temperature of room is going to reduce. From 29 it will go to 28 degrees centigrade, right? So this is a cyclic process. This is a cyclic process, and this will continue till this temperature also becomes equal to 25 degrees centigrade. So if this temperature and this temperature are equal, 25 minus 25, there is no difference between them. So what happens to the controller? This controller will tell your motor, just turn off, right? So this controller will turn off your motor. If the motor turns off, what happens to the compressor? The compressor will stop running, right? The compressor will stop running, and the room temperature might be constant here. But after some time, what happens again? The room temperature starts raising again because of some external environmental conditions, right? So if the temperature, as soon as the temperature raises from 25 degrees, let us say the temperature has raised to 26 degrees, right? So what happens again? When this is 26 degrees, this is again fed here. Again there is a negative value at the comparison. Then your controller will always, what will it do? Your controller will say to the motor, please start again and please run again, right? So this motor will start running again, and the compressor will run again, and the temperature is again brought down to what value? Again brought down to 25 degrees centigrade, right? So automatically, as soon as the temperature decreases, the controller is acting again to bring the temperature to 25 degrees centigrade again, right? So this is a cyclic process, and this is an automatic process. Let us say you have a small room confined, right? So confined to some 10, let us say some 1500 square feet. Not 1500 square feet is so large. Some 100 square feet room. You have some 100 square feet room, let us say, right? So in that room you have turned on your AC. You have turned on your AC, right? So initially there was only one person in the room. The desired temperature 25 degrees has been reached. But now what happened is, all of a sudden, nearly 10 to 15 people had rushed into your room. All of a sudden, 10 to 15 people had rushed into your room, right? If all of a sudden these many people rush into your room, what happens to the room temperature? They blow some hot air, right? So they exhale some hot air. Because of that hot air, what happens to the room temperature? Room temperature again goes up, right? As the room temperature increases, your AC, what does it do? It will run the compressor. It will continuously run the compressor, and it will bring down the room temperature to 25 degrees centigrade again. It will bring down the room temperature to 25 degrees centigrade back again. So all this process, this is automatic or not? Tell me the answer. All this process is automatic or not? Your AC is working automatically or not? Yes, AC is automatic, right? So all this is what? This is automatic, right? So yes, it is automatic, right? So this is an automatic control system. So we are usually interested in building up automatic control systems only, right? So you have went to shop something, right? You have went to buy some electronic product for your home, right? There you see some manual washing machines and some automatic washing machines. Which one will you prefer? You will obviously prefer the automatic washing machine only, because everyone wants automation. Everyone wants things to be automatically done, right? Without human interference, right? All the things should be done automatically, right? So throughout our control systems lectures, we will be focusing on analysis and design of automatic control systems only, right? So we will be focusing on what? We will be focusing on automatic control systems only, right? So from this block diagram, let us interpret what are the basic components of any automatic control system, right? What are the basic components of any automatic control system, right? So see here, what is this part? This part is called as what? This is comparator. Comparator, right? Any automatic control system needs a comparator, right? Can we control automatic system? Yes, Shubham Goyal, this automatic control system is behaving as per your inputs only, right? So you have asked it to run at 25 degrees centigrade only, it will give you 25 degrees centigrade only. If you input some 18 degrees centigrade, if you give some 18 degrees centigrade, it will give you that 18 degrees centigrade only. Did you get it? Right? So it has a comparator, right? So after comparator, what is the next stage? Next stage is controller, right? So after controller, what is the next stage? There is a device which gives mechanical power to your system, mechanical power to your plant, right? So the next one is, you can call it as actuator. Actuator, right? So compressor is the process, right? So initially this control theory was used in industrial automation, right? In chemical process control. So that is the reason why this process, whatever we have, that is called as plant or process. Plant or process. They have given a particular name in the beginning itself, so that name continued. That's it, right? So this is plant or process. What is the other component? We are having a temperature sensor. It is feeding back the output to the input stage. This sensor is feeding back the output to input stage, which means this is a feedback element. What is this? This is a feedback element. This is a feedback element, right? So let us be familiar with the control system terminology, right? So we have a controller, we have an actuator, we have a plant or process, we have a feedback element. In any automatic control system, we will be having all these components, right? In any automatic control system, what we will be having? We will be having all these components, right? So we have specific names to the signals also, right? This is called as input signal. Input signal, whereas this is called as output signal. This is output signal, right? So this, the signal from this feedback element is called as feedback signal. Feedback signal, right? Feedback signal, right? So the next, so the difference between input signal and feedback signal computed here, this is called as error. This is called as error. So the next thing is controller. After the controller, you are going to get a controlled variable. Controlled variable, right? Upon controlling this particular variable, you are able to control the actuator, right? So the signal after the actuator stage is called as actuator signal, right? Actuator signal, right? Finally, you are getting the output. You can also call this output as manipulated variable. What is this called as? Manipulated variable. manipulated variable. So using all this process, using this entire process, you are manipulating a particular output variable, right? So that is called as what? A manipulated variable. Your output is called as a manipulated variable, right? So this is the basic structure of any automatic control system, right? Whether it is your air conditioner, whether it is a cruise missile, right? Whether it is your anti-lock braking system in your bikes, right? So all these are having these components. They will be definitely having these components, right? See, there is input signal and the output converted into the domain of input, right? So let us say input signal is some displacement, right? Output is again transduced into that displacement only using this feedback element, right? So input and output are compared, right? The difference between input and output is nothing but error here, right? Input and output are compared and the difference between input and output is nothing but error, right? So any particular system is going to have all these parts in its control system. Is it clear, everyone? So let us define a basic structure of any particular control system, right? So we are defining a basic structure for this particular control system. Let us say these three blocks, right? Controller, motor, controller, actuator, as well as plant or process. We are combining these three into a single block. We are combining these three into a single block, that is G of S. We will simply call it as plant, right? So we will simply call it as plant or process, right? So again, we should have some feedback block. We will be indicating this feedback block with H of S. There should be a comparator. There should be a comparator stage, right? So input we generally designate with R of S. In time domain it is R of T, right? Output we generally designate with C of S. In time domain it is C of T, right? So the feedback signal we generally designate this with B of S, right? In time domain it is small b of t, right? The difference between R of t and B of t we will be designating E of t, and in S domain it is E of S. Is it clear? So this is the basic structure of any particular control system, right? So here, see here, so this is the generalized form of any negative feedback system. Why did I call it as a negative feedback system? See here, the feedback signal is being deducted from that of input, right? So the input has a positive sign, whereas the feedback signal has a negative sign, right? That is the reason why we are calling it as a negative feedback system, right? So see here, this is the general structure of any negative feedback system, right? So you can call it as block diagram of a negative feedback signal. Sorry, a negative feedback system. Block diagram of a particular negative feedback system. A negative feedback system. This is the general structure of any negative feedback system, right? So we generally use negative feedback just because we have seen how we are comparing two quantities, right? So by computing the difference, we are comparing two quantities, right? So block diagram of see, we are indicating these things in blocks, and that is the reason why this is called as a block diagram, right? So in many cases we'll use these block diagrams, and we'll see the block diagram reduction techniques and all these things. So see, one more thing is, you can also use a positive feedback here. Instead of a negative feedback, you can use a positive feedback also, and you can design logic for that particular system also, right? So you can also use positive feedback. If there is a plus sign here, what is it? It is a positive feedback system. If there is a plus sign here at the feedback signal, this will be a positive feedback system, right? So one important note you should note here is, one important point you should note here is, positive feedback systems, please note it down, positive feedback systems are comparatively unstable. Right? You will see why positive feedback systems are comparatively unstable when, kindly open the lecture tool link after the break to view the access. Okay. So you will see you will see why the systems, why positive feedback systems are comparatively unstable while you study inverse root locus in this root locus chapter. You will see more specifically, you will come to understand more specifically why they are comparatively unstable. But for now, let us note the positive feedback systems are what? Comparatively unstable. So in order to analyze, we generally consider only the stable systems. Therefore, we generally consider negative feedback systems for analysis, right? So what do we consider? We generally consider negative feedback systems for analysis. So generally throughout this lecture, we will use only negative feedback systems for analysis, right? But it is not like positive feedback systems are never useful, right? Positive feedback systems are useful in some cases, right? Can you give me an example of a positive feedback system you generally use in your laboratories? Can you tell me an example of a positive feedback system you generally use in your laboratories? Yes, oscillator circuits, right? So oscillator circuits, where do we use these oscillator circuits? See, where do we generally use these oscillator circuit? We'll use a crystal oscillator. Crystal oscillator is not a feedback system actually, right? We'll use a crystal oscillator to give the clock frequency, clock signal to your microprocessors, microcontrollers, right? So you will use a Smith trigger. Smith trigger is nothing but it is a positive feedback system, right? So Smith trigger can also be used as an oscillator, right? So these things are the systems designed by you, right? So there is one more natural positive feedback system, right? So you won't come out of your mother's womb if that entire system, that delivery of a baby isn't a positive feedback scenario. If that is not a positive feedback scenario, then you won't be coming out of your mother's womb, right? So just search for this in the net, right, in the internet, right? So just search for this question: why delivery of a child, why delivery of a child is a positive feedback system. Just search for this on the internet. Why delivery of a child is a positive feedback system. You will come to know an important discovery which you have never seen till now, right? Just search for this. Why delivery of a child is a positive feedback system. This is a natural control system which is an example of a perfect positive feedback system. It is useful also, right?